Good morning. Thank you for this opportunity to present today. So we have no relevant disclosures other than the fact that I am an engineer. So while this talk will be a little bit technical, bear with me and I'll hit all the clinical points throughout it. So it's no surprise that there are a lot of hernia meshes, and there's a lot of variation between these meshes in terms of material, absorbable, permanent, synthetic, etc. And mechanical properties are another important one. And we really don't know how these mechanical properties affect the abdominal wall because we haven't thus far had a technique to elucidate the effects at the mesh level, at this subsurface level. So what we sought out to do was determine how mesh mechanical properties affects tissue mechanics as a function of both time and pressure. We want to better understand the relationship between native tissue and mesh properties. We hypothesized that a mesh with dissimilar properties to the native abdominal wall will alter tissue mechanics more than a mesh with similar properties. So we have three main groups for our study. We used a porcine model. So the first group was native porcine tissue. Then we have our meshes. And then we have these two treatment groups, mesh A and mesh B, which we implanted into our porcine model. These meshes were chosen based on their physical and mechanical properties. So the similarities, they were all heavyweight, non-coated polypropylene meshes. We wanted them to be the same for their physical properties, but they differ in terms of their mechanics. Mesh A differs more than mesh B from native abdominal wall mechanics. So these two treatment groups underwent our in vivo fluoroscopic imaging analysis, whereas all three groups underwent our ex vivo mechanical testing. So for our treatment groups, on day -21, if you will, we created hernias by incising the fascia down to the peritoneum and allowing them a period to mature. At which time point we used open ventral recto rectus repair using our meshes, either mesh A or mesh B, and we had sutured stainless steel radio-opaque beads on the mesh, as you can see in the image below. Now this was for our imaging technique, which I'll explain a little bit. At this point, we also used titanium tacks in the periphery of the abdominal wall to track that peripheral tissue outside of the mesh as well. So we insufflated the abdominal wall between 5 and 30 millimeters of mercury and took images at each pressure and time point across day 0, day 7, and again at day 28. At this time, we also euthanized the animals and subjected the abdominal walls to mechanical testing. So with this in vivo imaging, what we really did was take two images at each time point and each pressure point, and they were at different angles, and we tracked the mesh using a MATLAB code over each image set. We were able to 3D reconstruct the abdominal wall, and through this, we were able to study areal strain over time and pressure. So for our ex vivo biaxial testing, we use this biaxial method, or simply testing in two directions, in order to test the stiffness of transverse and craniocaudal. This is a much more clinically relevant test method because in vivo forces and strains really don't occur in just one direction. We also studied the anisotropy, or simply the ratio of stiffness in the transverse versus craniocaudal directions. Now, this test method was for our meshes alone, for native tissue, and for those two treatment groups of ingrown explanted tissue at 28 days. So what we saw in vivo was that as a function of pressure, meshes expanded. They expanded about 3%, and there were no differences between mesh A and mesh B. Red indicates expansion, or greater than one areal stretch, whereas the blue indicates contraction, or a mesh shrinkage, if you will. Over time, we did see that the meshes contracted. They contracted anywhere between 0 and 30%. Now let's dive a little bit deeper into that mesh contracture. So these are just some example images from mesh A on day 7 and day 28. So we have the thick black line, which represents the mesh edge. Inside of that is the mesh. This is a top-down view. And then the red expansion on the periphery is from those titanium tacks that we implanted peripherally to the mesh. So the main difference between 7 and 28 you can really see is the stark difference between the blue and the red, or the shrinkage, the contracture, and the expansion of the peripheral abdominal wall. Now, clinically, we know that a lot of hernias fail at this mesh edge due to insufficient mesh overlap. So this is going to be important to look at potential stress concentrations at this mesh edge, the stark difference between the expansion and the contracture. Mesh B, on the other hand, did not see quite such drastic differences. There's a little bit of expansion, a little bit of contracture, and then looking group by group, data point by data point, we see that mesh A trends toward contracting more than mesh B. So for our ex vivo biaxial mechanics, let's first look at our control groups. So we see that the native tissue is about 7 newtons per millimeter. What does that mean? Not much right now, but you can see that mesh A is about twice as stiff as the native properties, and mesh B exhibits no stiffness differences. So mesh A is a little bit of a worse match in terms of stiffness properties. And those are the meshes alone. Now when we go and introduce our treatment groups, we see that both the mesh A tissue complex and the mesh B tissue complex are stiffer than either the meshes alone or native tissue. In addition, you see this stepwise increase. So mesh A really matches the mesh A tissue complex, while mesh B really matches the mesh B tissue complex. So we see that the repaired tissue begins to take on the properties of the mesh over time. Now this is just in the cranial-caudal direction, but the same significance and trends were exhibited in both directions for our biaxial testing. And then the next parameter is anisotropy. And again, this is a directional dependence, so it's just the transverse stiffness as a ratio to the cranial-caudal stiffness. And this is an important clinical parameter to look at because while each section of the abdominal wall may exhibit similar stiffnesses in different areas, each section of the abdominal wall truly exhibits a unique anisotropy ratio based on those different stiffnesses. So the rectus area of the native abdominal wall in a full thickness rectus sample is 2 as an anisotropy ratio. This simply means that the transverse direction is twice as stiff as the cranial-caudal direction. Mesh A, on the other hand, is nearly isotropic, or the same in all directions, and then mesh B is somewhere in between those. So again, we introduce our treatment groups after a period of 28 days explanted mesh tissue complexes, and we see that they really start to take on those mesh properties. We see tissue mesh complexes that are a lot more isotropic in nature, or that better match the mesh that was implanted over a period of time. So in summary, we have developed a novel technique. We can visualize the mesh in 3D at the mesh level, this subsurface level, which really hasn't been studied before. We see differences in contraction, and this shows a potential for stress concentrations at the mesh edges, which clinically we know is where a lot of failures occur. We see that repaired tissue really adopts the mesh properties and begins to take on those properties ex vivo. So what we believe is by matching mesh design to the native abdominal wall properties, we could potentially reduce changes in tissue. This could ultimately lead to reducing stress concentrations, and these stress concentrations could weaken the abdominal wall. Thank you.
Go ahead. Yeah. So my question is, you guys chose very similar meshes for the studies. I think it's actually really fascinating stuff. What accounts for the differences? Is it difference in the weaving pattern, the thickness of the polypropylene fiber? What were the differences between the meshes you could?
Both of those were, pretty much hit it on the head there. It's the weaving patterns are a little bit different, and in one direction for mesh A, they were just a little bit stiffer, a little bit thicker. They're really same, pore size, same every other physical properties. So the fact that there are these stark mechanical differences is kind of surprising, and it's something that's not really well known in the community yet. And I think that, it's mainly just the weave and the way that it's fabricated. But there's tons of different meshes out there, and every single mesh exhibits unique mechanical properties.
Mm-hmm.
Would you recommend to surgeons to use meshes which are more oriented longitudinally versus transversely towards anisotropic of 2, like you found for the native tissue?
I'm sorry, do you mind repeating the question?
You found that for the native tissue, the anisotropy is 2, right?
Yes.
So would you suggest to design a mesh or to implant a mesh which has similar anisotropic properties?
I think at this point, clinically, we can't really fully answer that question, but intuitively and based on preliminary results, shown today, I think that having an anisotropy ratio of the mesh that matches the tissue, could potentially reduce these changes. The one thing that really need to consider is that each abdominal wall section has different anisotropy ratios. I think I actually so the lateral section of the abdominal wall is pretty isotropic, even though in certain directions it exhibits the same stiffness as the native rectus area. And then below the arcuate line is again anisotropic. So, potentially, you know, in the future, we could design meshes that match different sections of the abdominal wall for different kinds of hernia repairs.
Great work.
Great. Thanks very much. Appreciate it.